Welcome to a new episode of Machine Learning Made Simple. A lot has happened since last week. In our previous episode, we explored AI agents and agentic workflows, specifically how automated workflows using AI agentic frameworks are transforming web browsing and other architectures. One of the earliest web browsing agents, Agent E, demonstrated how these frameworks could automate complex browsing tasks, paving the way for innovations like Claude's computer use, which achieved human-level visual recognition. In fact, if you give it some task like go and find the stock price of Apple and you pull up the browser in front of it, then it can look at the screen, find and navigate the browser and go to the Yahoo stock ticker for Apple and download the data. So it can do an autonomous traversing of the browser in front of it. And this progress also led to the emergence of AutoGPT, which is a more automated form of this. Here it essentially doesn't have an access to the whole browser and doesn't have the visual capability, but we saw that if we can create those tasks for it in a drag and drop fashion, it can go ahead and do those things. And the other one was Skyvern. Skyvern was just like Claude, but open source. If we give it a task, create an itinerary for traveling to Hawaii based on my taste, or book a flight or book a hotel and complete my itinerary for my visit to Hawaii for these days, let's say in December or January, whenever we are traveling. So Skyvern can do all those things in an automated fashion. Of course, there are hiccups and there are issues. It cannot interact with the on-screen elements in a very fine-grained fashion. And this progress eventually led to a new generations of these web and screen interacting agents that we are seeing. And one of the biggest ones that we are seeing right now is Manus, and we're going to talk about that. Another open source version has been just released from Microsoft, and that is called OmniParser 2. OmniParser version 2 is a completely open source. It offers an intuitive visual approach to automation. While AutoGPT was mostly drag and drop and hadn't have the vision capability, OmniParser has had this fine-grained capability of interacting with the screen, and it not only just interacts with the browser, it interacts with everything that is sees on the screen, and we're going to talk about that in more detail. But the biggest news for this last week was Manus, that was released by this company from China. They have a few use cases that they deployed and demonstrated on their front page, and if we look at that, we can see Manus has all these fully automated fully autonomous AI agents that can go out and do the task. Looks like it's not doing a lot, but that's getting people excited because this is the frontier. We are going towards that fully autonomous AI agent that can book our itinerary or perform that market research marketer needs, increase productivity almost 100 to 200 times. That being said, we're not going to dive too much deep into Manus for now because it's not accessible. We cannot test it out right now. There's so many things that we still need to know. So we're going to dive deep into OmniParser 2, which is open source, which we can see what it can do, and that actually forms a basis of the screen interacting agents that we are seeing right now. But our main story really is the biggest news, and most people probably even haven't noticed it. It's the diffusion large language model. This is a counterpart of large transformer based large language models that we have used to seeing, like the GPT-4 models or the Claude Sonnet series of models, or even Llama 3. Now, this is a new generation of models which supersedes all those transformer-based models. And the great news of this new series of diffusion-based large language model is that they can generate code at 100 times the speed of the GPT-4 model. Yes, it can, and I'm going to demonstrate that they can generate code at least 5 to 10 times than GPT-4. Maybe not as fast as the Sonnet model, but we have to still see if the code is coherent and if it doesn't hallucinate. And that's a separate topic for another day. So let's get started. We'll first talk about OmniParser 2, and then we'll talk about the diffusion-based large language model. Microsoft just dropped a game changer, an AI agent which can perform human-like tasks with just a simple text command. Imagine typing buy milk and the AI navigates a browser, finds the right item, it places the order and checks out all on its own, or methodically pull all the Git repos that you have. GitHub repos, if you are not familiar with the coding terminology, is where programmers store all their codes, and it's very easy to sync codes both from the offline to the online repository. So essentially, when we perform a Git pull, it pulls all the codes that in the online repository and syncs with the local repository and keeps them synced over time. So if we just say that clone the git repo, it will methodically find the browser, go to the URL and start looking for the button which says clone the GitHub repository. And once it finds the button which allows it to clone the GitHub repository, then it will copy that text and then copy the text and places in the terminal, and the terminal will just clone the GitHub repo. So this is not a future concept. OmniPursor is here, and it's a Microsoft take on AI powered screen control. It essentially uses a multimodal vision model to see the UI and elements and interact with them intelligently, and it has a very fine grained control. Think the Claude's computer user agent much better. It offers more granular screen element detection and smoother automation. Let's be real, giving an AI full control of our screen is still a security risk. If you have been following us, we explored this tech in episode 64 with Claude's agent, where we described all the agentic framework, and in that context we talked about the first use case of using the agentic framework was using a web browsing agent, and this is where we are, where a web agent can autonomously take a task and browse the web and perform the task on our behalf. If you want to test it live, let us know. For our main story today, we're diving into the diffusion large language models. This is the AI breakthrough that's taking the research world by storm. These models aren't just another incremental improvement, they represent a fundamental shift in how AI generates text. And here's the kicker, they are blazingly fast. In some cases, they can generate code and entire code bases and text up to 100 times faster than the traditional autoregressive models like GPT. And they are so fast that they can produce text before you can blink, and it's even faster than the Claude generation of models. For years, the autoregressive models have been the backbone of AI generated text. They work by predicting the next token, and in some cases just doing one step at a time in a left to right sequence. It's effective but really slow, especially for long form text and complex reasoning. Diffusion models take a completely different approach. Instead of generating words sequentially like the autoregressive models do, they start with pure noise and then refine the entire sequence in parallel, reconstructing sentences through a step-by-step denoising process. The idea of using diffusion for text isn't entirely new, but it's only recently become practical. A handful of research breakthroughs, starting with Google's D3PM in 2021, followed by DeepMind's mask diffusion models, MD4 in 2024, has laid the groundwork. But the real game changer is LLaDA, L-L-A-D-A, the first large-scale diffusion-based large language model that competes with GPT-style models in speed, fluency, and even reasoning tasks. Today, we are going to break down exactly how these diffusion large language models work, why they are so fast, and whether they could replace the traditional large language models altogether, which seems very likely. Could this be the end of the autoregression models as we know it? Let's find out. So let's start by understanding how the diffusion process actually works. In image generation, diffusion models follow a simple but very powerful idea. Start with a clear image and gradually add noise over many steps until the image is nothing but static. By static, we mean pure noise. Then we train a model to reverse this process step by step until the original image is reconstructed. So we start with an image, convert that to pure Gaussian noise. We re-extract the image back from that noise that we have created. So we have created a reversible process that we can go both ways. And the beauty of this method is that if we train a machine learning algorithm to learn this process both going backwards and frontwards, so if it learns how to create an image from noise and vice versa, convert an image to noise, then it can go both ways. For example, if we ask it to create the image of a cat playing an ukulele, it can create that image from pure noise. All he has to do is sample the noise space or the Gaussian space where it knows that noise is adjacent or represent all that noise in that region in the latent space, represent cat playing an ukulele, and it can pick from there and reconstruct an image of a cat from almost nothing. And the key advantage is, unlike GANs or the general adversarial networks, which usually generate the entire image at once, these diffusion models create the images by progressive refinements, and which makes them more stable, and they are capable of generating highly detailed and high resolution images. And that's why GANs fell out of favor. Even though they can reconstruct highly detailed and accurate images, GANs are very unstable because they try to generate the entire image from the latent space at once. The beauty of the diffusion model is that due to that diffusion process, which is the lengthy denoising process, we can add more noise at every level of detail. In fact, that is done in StyleGAN, and we covered StyleGAN in an earlier episode. I'll post a link if you're interested to look at it. The way it works is that, let's say we create an image of a cat playing a ukulele with some noise, but if we decided, okay, we need a little bit more detail on the cat's hair, maybe we want the cat's furs to show and be more detailed. So maybe after the image is slightly in a level of denoised form, like halfway through, then we can add some extra noise. Tell the network which is generating is like, this is extra noise I'm adding, more fine grain detail I'm adding, create these to create the furs of the cat. So we can add more data and make the image more detailed. This is called high frequency data that's being added. So the reason this works so well is that the image exists in a continuous space pixel values, which can be adjusted in small increments, and noise can be mathematically modeled as a normal distribution. And if you're familiar with it, it's essentially a Gaussian distribution, which this allows the diffusion models to smoothly denoise the images by predicting and removing continuous noise at each step. But when it comes to text, it becomes slightly more tricky, because for text is not continuous. The words aren't continuous. They're discrete symbols which has to be chosen from a fixed vocabulary. We cannot just corrupt a word by shifting its value slightly like you can with a pixel. Instead, we need a discrete diffusion model that can replace words and characters step by step. So essentially the whole idea is that we are pushing the model towards what we expect. Let's say the picture of a portrait of Mona Lisa, or if you want to create a cat playing an ukulele in that style, the picture of Mona Lisa has a certain stylistic representation that we understand as a human being. But what is the mathematical idea of that stylistic representation? It has latent representation, a mathematical representation which represents the stylistic form of Mona Lisa, and we can capture that by slowly pushing that noise towards that stylistic probabilistic distribution. So we can start with pure Gaussian noise which has some probabilistic distribution, and we can slowly push it towards the stylistic latent representation of Mona Lisa or those kind of pictures by Da Vinci by doing something known as training a loss function of the Keil divergence. So the Keil divergence essentially measures the difference between two distributions. So let's say your distribution is pure noise and you essentially want to go to the distribution which represents the probability distribution, which represents the stylistic information of Mona Lisa. Then you calculate the difference between those probability distributions, and if the difference is large, which will be because if you're starting with noise, and we slowly push the network to converge them, force the image that we are generating, that image's distribution to slowly represent or look like the stylistic distribution of Mona Lisa, so that they finally match. And essentially that's the whole process of the diffusion process. Now for discrete, that becomes slightly tricky because we cannot start with a continuous distribution if the final distribution is not fully continuous. So we can start with a discrete uniform distribution, or we can start with some kind of discretized Gaussian version. So that becomes slightly tricky. We'll take a deep dive into that paper if you're interested in a separate, but here we'll just keep it short. So this is exactly what the discrete noise diffusion probabilistic models are doing. So instead of adding the Gaussian noise, they just apply the structured corruption process where the words get masked, replaced, or scrambled in a controlled way. The goal is to essentially learn how to reverse this structured noise process, recovering meaningful text step by step. Just like how image diffusion model reconstruct a picture, in the same way the diffusion code generator or diffusion large language model will start generating code from latent representation and start with random words and completely generate the full text and a full-fledged game from scratch within like seconds, or a blink of an eye, in milliseconds. And the reason they can do that is because they start with the latent representation, the idea of what the game should look like, and the code this just emerges from it. Just like if we have to write a code from Quicksort, we don't memorize what is Quicksort. We have a latent understanding of the algorithm. For example, Quicksort is the fastest sorting algorithm. Let's say we are doing coding interviews. We don't memorize the Quicksort. Some people do, but most people understand how Quicksort works. And then they store the latent representation in their brain, and then they can reproduce in any language, not just Python, because with Python you have to memorize the steps. But if they have a latent representation, a deeper understanding how the algorithm works, they can reproduce it in different languages, Java, JavaScript, Python, any language you'll ask a person who has a deeper understanding of how the algorithm works, they can do it. And the same thing is happening here, and that's very interesting and also concerning at the same time. It is very mind-boggling, like an emergent phenomenon where the latent representation of the code or the quicksort algorithm is learned, and it is emerging from that. In the same way we think and store information, we don't store the code, we don't memorize the code for quicksort or bubble sort or any kind of algorithm. We essentially have an understanding what the code does, and then we can recreate it from our understanding. So what we're doing, we're encoding the information about the semantic understanding of what the stored in algorithms or any algorithms we're trying to recreate in some kind of a semantic version, or some kind of a representation in our brain, and then we recreate from that. I believe that this denoising process, this discrete diffusion process, is also learning those latent representation and learning to recreate from that representation the word version of the latent representation. This is mind-boggling. This is probably going towards AGI, and machines will really understand the semantic meanings of things if they have not done it already. So the only tricky part here is that unlike continuous distribution, where we sample from a normal distribution, the discrete distribution requires sampling from a categorical distribution. So we'll not delve into that. We'll have a separate video on this. Keep an eye out for that. Now let's talk about the diffusion large language model, or which are codenamed LaDA for short. And these are extremely fast diffusion models, auto code generating models. And I demonstrated in the previous segment where I showed the same code generation prompt was given to GPT-4o, and this LaDA model, which is the front end for which was the Mercury, and the Mercury model generated the code 10 times faster than the GPT-4o model. Now, why are these models so great, and what is this LaDA breakthrough? So let's talk about it. Imagine AI models that can generate entire sentences at once instead of predicting one word at a time. That's exactly what LaDA does. It's a diffusion-based language model, which is now challenging the transformer-based models. LaDA builds on two key breakthroughs, and we're not going to go too detailed into that. I'll just mention it, what the breakthroughs are. One is called RADD, and other one is called scaling masked diffusion model. So these research models, they move beyond the traditional autoregressive models like GPT-4 and GPT. So, and the result is that a model which can match the performance of the best GPT style system while allowing faster parallelized generation. Imagine the whole code is being generated at once from a latent noisy description instead of going one token, one word by one word. So, but to understand why this is such a big deal, we first need to look at how the diffusion models differ from the traditional transformers. Most AI models today generate one token at a time. Think Llama or GPT-4, like typing out a message letter by letter. It is sequential. Each new word depends on the previous one. LaDA takes a completely different approach. Instead of building one text one step at a time, it fills in missing pieces all at once, like solving a crossword puzzle where you uncover multiple words at the same time. This means LaDA can generate text in parallel, leading to faster performance and even more flexible sentence structures. But to make this work, it needed to break through how diffusion models are trained, and this is where RAD comes in. To talk about RAD very briefly, imagine using an AI assistant you're using to edit a document. A basic AI might go step by step, fixing typos first, then grammar, then formatting, strictly following a predefined sequence of steps. But a smarter AI doesn't need to follow a fixed order. Instead, it looks at the entire document in a holistic fashion and decides what to fix first and makes the process faster and more optimized. And that's what RAD proved about masked diffusion models. They don't need a strict time-based process. Earlier diffusion models relied on a time step input, like you have to give time steps 0, 1, 2, 3, 4 to n in order for the model to follow that structure, the diffusion process from end to end, because you have to reverse it because it is a time-bound process. Essentially, if you're familiar with the language of differential equations, it's a diffusion process. So it is time-bound, it is differentiable with respect to time. Now, what RAD proved that, especially with these masked diffusion models, we don't need these kind of time-based systems. We don't need time. The time goes out of the window, and that's one of the greatest discoveries in the past few months, that we don't need time for these diffusion models. And what that means is that these models are now having have an equivalence to the transformer models. So essentially we are uncovering the latent theoretical framework for these transformer models, which are kind of worked ad hoc in an ad hoc fashion, but now people are figuring out what are the basic mathematical structures of these models are. So the beauty of this discovery is that since we don't need those time steps input to guide our generation, models can now infer the correct sequences on their own. And this discovery allowed the LADA to be built just like the GPT model. So for example, they can use the transformer architecture and don't have to build those mathematically cumbersome models. They can just use the transformer architecture, and that made it simpler, more efficient, and easier to scale, because transformer scales very well while keeping all the advantages of the diffusion models. So let's talk about how the scaling laws for these diffusion large language models and why the scaling laws are important. So one of the biggest challenges in AI research is scalability. Does a new idea work as well when scaled up to billions of parameters? So let's say a model can solve a problem. Let's say you have a trained model which can look at number plates and can extract the numbers. Now, can it do it for millions of number plates if we increase the model size? Can it? Maybe not. Sometimes it fails. So the mass diffusion model really tackled this question, or the scaled mass diffusion model tackled this question, introduced the first scaling law for the diffusion based large language models, and they proved that when they train with the same data and model size, they can perform as well as the GPT models. However, there is a slight difference because the diffusion models do need more parameters, at least now, because as we know that as research progresses, they become more and more optimized and need less and less parameters, which the same thing happened with other models as well. They become severely highly optimized by the researchers who are really resource constrained. But for now, the mass diffusion models need a lot of parameters, maybe 16 times or 32 times more parameters than the comparable their counterparts, autoregressive counterparts, which is the Llama 3 or Llama 3.2. However, the good news is that they show the same scaling laws, which means they show the same amount of improvement in performance with the same number of increase of parameters. So if, let's say, Llama 3 went from 32 billion to 405 billion with an 30% increase in performance, the same thing will apply to these mass diffusion models, which means that they're following the same scaling laws as these transformer based models. So this method is so effective that LADA adopted it directly and giving it an extra boost in accuracy. And the beauty of this diffusion based model is that instead of having that one mass word that BERT does, it can generate all the words simultaneously at the same time, almost instantly. That's what makes them so powerful, that they can generate it so fast, so quickly. Yes, they need 16 times more parameters than the regular, their autoregressive counterparts like BERT or GPT or Llama. However, they are also 10 to 100 times faster. So I'll take speed because they consume the same amount of power, a little bit more memory maybe. So this is a big deal because it matches the Llama 3 in all those benchmarks, MMLU, HELA-SWAG, Pika. In code generation, LADA is like, as I said, 100 times faster. In fact, I showed it in the previous segment that it's 100 times faster than GPT-4o. A task that requires reasoning over scrambled sentences, LADA definitely outperforms even GPT-4o. This is a big deal because it means the diffusion-based large language models aren't just an alternative, they are the competition. They are the ones which are going to replace these transformer-based models. Now, there is good news and bad news. The good news is that LADA is 100 times faster in code generation. The bad news, or kind of a bad news, is that LADA is still a kind of a small model. It's only 8 billion parameters. Now the question is, can LADA scale beyond these 8 billion parameters? Can it become 100 billion? Can it become 1 trillion parameter model like the GPT-4 series of models? They do match the traditional transformers in performance. They solve major weaknesses in reasoning. So when we compared those performances with the Llama, the LADA 8 billion was actually compared with the Llama 3 8 billion parameter model. It was not compared with the 405 billion parameter model, which would have been unfair. Now, but that being said, the code generation capability, as you saw, is 100 times faster. It's like no comparison there. So this is clearly the way to go. And the next big challenge, closing the compute efficiency gap. If that happens, we may see the AI industry shift away from these autoregressive models entirely. And what does that means for OpenAI? OpenAI's business model is definitely challenged by the DeepSeek models and other open source models, which are substantially great at their job. And now this new arrival, LADA, will totally transform. Of course, it may or may not transform. It might not scale that well. For example, the Mamba architecture didn't perform very well, even though it's a linearly scaling architecture. This LADA might fail. real, but for now, the speed at which it is generating code, it seems that it will really replace OpenAI as a code generation model, and we'll just wait and watch what happens. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.